This is section 2.3. Today we're going to learn a new method to solve differential equations, namely first order linear differential equations. So let's start by reviewing separation of variables, which is the method we learned last time. So if I want to separate the variables on this differential equation here, I'm going to move the xy over by subtraction, and now I'm going to move my y's to the left and my x's to the right, keep the negative sign with the x. And now that the variables are separated, I'm going to integrate both sides. Whoops, this should be a dy. On the left, I get ln, absolute value of y, and on the right, I get negative 1/2 x squared plus c. Now we're going to exponentiate both sides of this equation, and when I exponentiate, that allows me to get rid of the absolute value. And if you're confused about that, go back and watch the first part of the last section's lecture notes. So I can jump right to y equals a e to the negative 1/2 x squared. And a is plus or minus e to the c. That's how we got rid of the absolute value. Okay, here's the algorithm for solving a linear first order differential equation. 1, put the equation in standard form. This is standard form. Y prime plus p of xy equals q of x. 2, find an integrating factor. An integrating factor is something you multiply a differential equation by in order to integrate. And so that's where it gets its name. In this case, your integrating factor will be e to the integral of p of x dx. Take c, the constant of integration, to be 0. If there's an absolute value in mu, you can get rid of it, and I'll show you how to do that in example 2. That's not the same as getting rid of the absolute value up above. That was a difference. Step 3, you're magically going to jump to this equation. Mu y is the integral of mu q dx, and I will explain that magical step on the next page. Step 4, divide both sides by mu of x, so you're solving for y. Okay, here's an example. 1, equation's already in standard form, but let's write down p and q. P of x is x, q of x is 0. Step 2, our integrating factor is e to the integral of x dx, which is e to the 1/2 x squared. I'm taking the constant of integration to be 0. Step 3, I jump to the magic step. Mu y is the integral of mu q. So mu is e to the 1/2 x squared multiplied by y, and that's the integral of e to the 1/2 x squared times 0 dx. Now the integral of 0 is a constant, all right? And then step 4, divide both sides by e to the 1/2 x squared to solve for y. Now c over e to the 1/2 x squared, that's the same thing as multiplying both sides by e to the negative 1/2 x squared, and that looks a little bit better, so that's what I'm going to do. Same answer as we got before, except the a before is now called c, but since it's a constant, it doesn't matter what you call it. All right, let me explain this jump from step 2 to 3 with the next example. I'm going to solve this differential equation. Step 1, get it into standard form, and I do that by dividing both sides by x, and I've already done that. In this case, p of x will be the coefficient of y, but it has to be written as y prime plus p of xy. So this case, p is negative 2 over x. And then q is x squared cos x. Step 2, the integrating factor is e to the integral of negative 2 over x dx, which is e to the negative 2 ln of the absolute value of x. Now, before I can cancel the e and the log, I need to bring that negative 2 up as an exponent. E to the ln absolute, x to the negative 2 is 1 over x squared. And now I'm getting rid of the absolute value, not by anything fancy. It's just 1 over x squared is always positive. Now, let me explain jumping to step 3. So here's the step that you're usually going to skip. It's happening in the background. But what's happening is, if we take this equation here, and multiply by 1 over x squared, we get this equation here. Now this is rigged, this integrating factor is rigged so that this left-hand side is d by dx of 1 over x squared y, mu times y. All right, do the product rule and implicit differentiation, and you'll see that that's the case. Then we integrate both sides. So when you jump from step 2 to step 3, what's happening is you're integrating the derivative of mu y, and that's why every single time you'll get mu y. So you don't have to do that every time, because that's why we do this. So you can jump straight to step 3. Mu times y is the integral of cos x dx, which is sine x plus c. And then step 4, in this case, I'm going to multiply both sides by x squared. So y is x squared sine x plus x squared c. Now, if you're thinking, oh, before, if I had c and I multiplied by 2, I would just call that a new constant b. So if you're thinking, oh, I'll just call this b, don't do that. You can't. That only works when you're taking a constant and multiplying by another constant. But in this case, x squared is not constant, so you no longer have a constant. You can't just rename this guy. It's actually got to be written x squared c. Okay, now this example here is going to explain why you're allowed to get rid of the absolute value if you end up with 1 in your integrating factor. Step 1 is done. This is already in standard form, but let's identify p and q. P is negative 1 over x, and q is x e to the x. Step 2, our integrating factor, mu, is e to the integral of negative 1 over x dx, which is e to the negative ln absolute value of x. And I want to see that. I mean, whenever you drop your absolute value, I want to see that you're doing it up until the point that you're allowed to drop it. Like if you're doing separation of variables, I want to see that absolute value right there. I understand it goes away in the next step, but when you integrate, make sure you do it right, and there's an absolute value there. Same with this, there's an absolute value here, so I want to see that. Now that's e to the ln absolute 1 over x. Now, this is absolute 1 over x, but I am allowed to drop the absolute value and just use this as my integrating factor. And here's why. This is actually giving me 2 choices of integrating factor. If x is positive, then the absolute value of 1 over x is 1 over x. So step 3 would give me, I multiply both sides by 1 over x. And of course, this x cancels with that one, and I would just end up integrating e to the x dx. Now, if x is negative, then the absolute value of x is negative 1 over x. So step 3 would jump to multiplying both sides by negative 1 over x. Well, the minuses cancel anyway, because you're doing it on both sides. And then these x's cancel. I end up with the exact same thing as I ended up with by assuming x was positive. So you're allowed to go ahead and get rid of the absolute value. I'm just going to assume that my mu of x is 1 over x for my step 3, and go 1 over xy is the integral of e to the x dx, which is e to the x plus c. And then step 4, multiply both sides by x. Y is x e to the x plus xc. You can't call that b, it's xc. And now in this case, there's going to be a step 5 because I have an initial condition. So step 5, y of 1 is e minus 1. So on the left, put in e minus 1. And on the right, everywhere you see an x, put a 1. So that gives me e plus c. So that tells me c is negative 1. And my final answer is y equals x e to the x minus x. Let's do another example. It's already in standard form, so I just need to identify p and q. P is 6x, q is 12x. Step 2, my integrating factor, e to the integral of 6x dx is e to the 3x squared. Take the constant to be 0. Step 3, jump to the special equation, mu times y, that's e to the 3x squared times y, is the integral of mu q, which I'm going to put the 12x in front, 12x e to the 3x squared dx. Okay, this is a u sub. U is 3x squared, du is 6x dx. I have 12x dx, so 2 du is 12x dx. So this is twice the integral of e to the u du, which is 2 e to the u, I'm going to back substitute here, e to the 3x squared plus c. And then step 4, I'm going to divide both sides by e to the 3x squared. So y is 2. And then plus c over e to the 3x squared. I'm going to write that as c e to the negative 3x squared. Okay, that would be our answer, except that this is an initial value problem, so there's going to be a step 5. Y of 0 is negative 2. So negative 2 is 2 plus c. So c is negative 4. So my final answer is y is 2 minus 4 e to the negative 3x squared. Okay, next one, you try it. So pause the video, put this in standard form. You're going to have to write a dy dx because you want to solve for y eventually and see what you get. Okay, so step 1, hopefully you did that. First, I'm going to divide both sides by dx. So x plus y plus 1 minus dy over dx is 0. And now I'm going to write this in standard form. Dy dx minus y is x plus 1. So my p is negative 1, and my q is x plus 1. So step 2, my integrating factor, e to the integral of negative 1 dx is e to the negative x. Step 3, mu y, so that's e to the negative x times y, is the integral of mu q. So I get e to the negative x times x plus 1. I'll put the x plus 1 first. Okay, so this is going to require integration by parts. So u is going to be x plus 1 dv. And when you do parts, I want to see this chart, four items. U and dv go on the top. This is e to the negative x dx. To get du, we differentiate. That's dx. And to get v, we integrate. Negative e to the negative x. And so now I want uv minus the integral of v du. So uv is negative x plus 1 e to the negative x, and I want to subtract the integral of v du. V is negative, so I'll just make that a positive. All right, and then that's a pretty easy integral. Negative x plus 1 e to the negative x minus e to the negative x plus c. Step 4, so I get y equals negative x plus 1 minus 1 plus ce to the positive x. And then just a little bit of cleanup, combine like terms, negative x minus 2 plus ce to the positive x. So hopefully you guys all got that as your answer. Okay, one more problem we'll do together. First, I want to mention existence and uniqueness theorem. Yes, there's another one, but this one is for differential equations that are linear and first order. So here's an example. We're not using the EUT, but I do want to explain some things as we go. First of all, when you put an equation into standard form, you might lose some solutions. In this case, we're not going to lose solutions, but you might, because the first step here is to divide through by x. So we get y prime minus 1 over x, y equals 1. When you divide by x, you're assuming that x is not 0, right? But what if x equal to 0 were a solution? Then you might miss that solution at the end. So it's something to keep in mind. So my p is negative 1 over x, and my q is 1. Now, when I divide by x, I have to assume that x is not 0, so I have to make a decision. Either x is going to be positive or x is going to be negative. I can't have both, all right? I need my coefficients to be continuous, and they're not continuous here at 0. So I'm either going to have to pick the left-hand side of the number line or the right-hand side. I always pick positive if I'm given a choice, but if you're given an initial value problem, you're not given a choice. Y of 1 is 11. Well, 1 is over here. So the choice has been made for us. We're assuming x is positive. So step 2, mu equals e to the integral of negative 1 over x dx, which is e to the negative ln of the absolute value of x, which is e to the ln absolute 1 over x. But x is positive, so that's 1 over x. And even if I weren't assuming that, I'm allowed to drop the absolute value when I do my mu anyway. Okay, step 3, mu y, so 1 over xy, is the integral of mu q, 1 over x, dx, which is ln of the absolute value of x plus c. Now, it is true that we're assuming x is positive, so I'm going to drop that absolute value in a minute. Step 4, y is x ln, I'll drop my absolute value, x plus cx. And then step 5, this is an initial value problem, so there is a step 5. Put 11 in for y and 1 in for x. So 1 times ln of 1 plus c times 1. ln of 1 is 0, so c is 11. Y equals x ln x plus 11x is our final answer. Good times. All right, that's the end of this section.